I know it best as the dot product. That's when I learned it. That's what it was called the most. But it has three different names: inner product, dot product, scalar product. The use of the word scalar product is nice because the answer is just a number, not a vector. So since the answer is a scalar, using the word scalar product is nice. I learned it as dot product because you show it by drawing a dot in between. And I was like, oh yeah, that's the one with the dot in between. I don't know how inner product is helpful for any remembrances off the top of my head. Okay, but yeah, still not very helpful. Okay, and the dot product is kind of like matrix multiplication, except if you have two vectors in 2 dimensions, oh, I should use different numbers just for fun. The top numbers get, like, you know how in matrices you had to turn one and then crash them in? In vectors, it's already turned, because you're either working in 2 dimensions or 3 dimensions, and you just multiply the first numbers, multiply the second numbers, add them together. So the dot product of these two would be 31. Same thing in 3 dimensions. Multiply the first ones, multiply the second ones, multiply the third ones, and add them up. So here, find the scalar product of, so I have 2, negative 3, dot 1, 2. 2 times 1 is 2. Negative 3 times 2 is negative 6. Add them together, and we have a dot product of negative 4. 3 dimensions, also easy to find dot products. So our first vector, 2, negative 5, 3, dot product with 4, 1, negative 7. 2 times 4 is 8. Negative 5 times 1, negative 5. 3 times negative 7, negative 21. Negative 18. Now, why the dot, like it's the math in both 2 dimensions and 3 dimensions is simple. Okay? Yay! Why do we have the dot product? What does it tell us? Okay? So first, we're going to look at some properties. Does it make sense that you can do the dot product in both ways and the order doesn't matter? Because you're multiplying tops, multiplying bottoms, adding them together. Order doesn't matter. If you have another number out in front of your vector, you can do the dot product first, or you can multiply it in the first one, or you can multiply it in the second one. That follows your regular rules for numbers as well. If you have the dot product of adding, you could distribute the dot product. And the dot product with the 0 vector is 0. So these act very much like numbers, and you can choose to do any of your number rules in any order, which is kind of nice with the dot product. But we've learned with matrices that sometimes now can't necessarily multiply same order, so there are different rules. But for the dot product, things seem to work just like numbers. Now here is some fascinating things that come out of the dot product. If you do the dot product with something that is itself, so for example, if my vector is, let's do a nice easy one, 3, 4, and I do the dot product with 3, 4 again, I'm going to get 9 plus 16, which is 25. And if you think about the vector 3, 4. That makes your 3, 4, 5 triangle. The length of that would be 5. And when I do the dot product, I get 25, which is just the length squared, because it does the a squared plus b squared. Okay? I mean, you could do a squared plus b squared equals c squared. This isn't really finding us anything super important, but this one is where things get very powerful. It just so happens that the dot product of two vectors is equal to the length of the one vector times the length of the other vector times cosine of the angle between the two vectors. This is really simple math that we just did. The result is substantial. Okay? What is the angle between vectors that are the same? 0 degrees. What is cos of 0 degrees? 1. Okay? So this will allow us to do mathematics in 2 dimensions and 3 dimensions that can replace your cosine law, sine law, a bunch of long formulas in a much simpler way. Yes. So let's say you had this vector and this vector. Okay? Do we want to do something that we actually know, or do we want to do something we don't know? Like let's start with one we don't know. Let's say this one looks like the vector I've gone 5 to the right, none up. And this one looks like I've gone 2 to the right and both the same length up, 5 up. Okay? The length of this one is 5. The length of this one is the square root of 29. So if we did the dot product of, I'll call this one u and this one v, u dot v happens to equal 10. 2 times 5 is 10. 5 plus 0 times 0 is 0. 10 plus 0 is 10. That 10 happens to equal the length of this one, which is 5, the length of this one, which we found out to be root 29, times cos of the angle theta, which I'll write in green and draw in green right there. So you want to find the angle there between those two? You now know that cos of theta is 10 over 5, root 29, and you could find that. Yes, the tail to tail is important, and so that's written right here. So you have to draw your vectors tail to tail. Yeah, if you're drawing them one pass onto another to make a resultant vector, it doesn't make sense. So you could now easily figure out what theta is. Okay? How would we have to do this in, if you had this in regular geometry, you would basically say you have a triangle. You want to find this angle. I know this length is 5. I know this length is root 29, and because I have these points, I could do a squared plus b squared equals c squared with a different triangle, and I could find that. And then you'd have to use your formula that says cos theta is c squared minus a squared plus b squared all over negative 2ab or whatever. Probably had one of the negatives or positives mixed up in there. There is, if you rearrange it for cos theta. If you leave it how it is regular, the regular formula says that a squared equals b squared plus c squared minus 2bc cos theta. So there is a fraction when you solve for cos theta. This is much simpler than that. Plus, you don't have to calculate the third side. you replace it with a dot product, which is really simple. It is, but simplified. And the beautiful thing about it is that it works in 3 dimensions as well. So if 2 vectors are perpendicular, here is the new fun word for perpendicular, orthogonal, then the dot product would be 0. So now we have a much quicker way to tell if 2 things are perpendicular, right? Before, how would you tell if 2 things were perpendicular? You'd have to find the slopes, and if the slopes were negative reciprocals, then you could say, I know that they're perpendicular. Now, we just find the dot product if it's 0, because the only way it can be 0 is if cos of 90 degrees is 0, and the angle at 90 degrees is 90 degrees, which would make cos equal to 0, and then that whole thing is 0. When the angle between 2 vectors v and w, or u and v, or whichever letters you want, is acute, meaning less than 90 degrees, that means that cos has to be greater than 0, because cos in quadrant 1 is positive. And so your dot product has to be positive. If your dot product is positive, then the angle between your vectors is less than 90 degrees. If your dot product is negative, then the angle between your vectors has to go into quadrant 2. Because again, if we look at this formula, I'm just going to go back for a second, this is always positive, this is always positive, this is the only thing that can change to be either positive or negative. This is going to be positive in quadrant 1 and negative in quadrant 2 because of your cast rule. And so if you get something in quadrant 2, meaning the angle between the 2 vectors is more than 90 degrees, then the dot product will be negative. And we can rearrange this same formula to get cos theta by itself, which we did at the beginning, and now you can solve for the angle between 2 vectors really easily and quickly. And when you go to 3 dimensions, this would have been possible, but time-consuming using your math up till now. You have 2 vectors in 3 dimensions. If we do the dot product of these 2, we would get 12 minus 2 plus 2 equals 12. Right away, I know that the angle between these 2 vectors is between 0 and 90 degrees. And if I want to find the angle, cos of theta will equal the dot product over, okay. Technically, what in my formula, I didn't do a symbol between them. I just wrote them beside each other, right? Math. Okay? Because the bottom is multiplied. And I kind of wanted to put a dot in between, but now a dot means something different. It would technically be okay on the bottom because the bottom would be multiplying 2 scalars, which therefore a dot product doesn't exist. And here we have 2 vectors, in which case the dot is the dot product, or the scalar product. So we already figured out that u dot v was 12. What's the length of u? 9 plus 4 plus 1, square root of 13. What's the length of, w in this case? 16 plus 1, plus 4, 21. And we can go to our calculator and do cos inverse of 12 divided by 9. Yes, 14. Thank you. And depending if you're in radians or degrees, 45.58 degrees. Mm-hmm.
For this question, how you know that this angle should be less than 90 degrees?
Because the dot product is positive, and then thinking back here, if cos is positive, it's in quadrant 1. If cos is negative, it's in quadrant 2. So the fact that they tell us that these are perpendicular or orthogonal, we know that the dot product is equal to 0. The one vector is 2m, m, and 8. The other vector is 1, 3m, and minus 1. So the dot product between these two is 2m plus 3m squared minus 8. So 3m squared plus 2m minus 8 has to equal 0. See if we can factor this nicely. I'm going to go 4 here, 2 there, plus, minus. Every time you factor, you should multiply it out quickly in your head just to make sure that it works out. And so we have two possibilities for m. M could be 4/3, or m could be negative 2. Mm-hmm. We multiply. No, because if I multiply this, minus 4, plus 6, no problem. I would question me too based on my track record. Mm-hmm. It's all, I would love to create a mathematics that would make sense up until the last piece of information, in which case everything falls apart. But you could teach a whole unit. Yeah, okay, yeah, that makes sense. That makes sense. He's tried to. Not a good idea. Yeah, he said that the fallout afterwards didn't go so well. Yeah. The whole purpose of you should question your teacher, although good, maybe not taken to that extent. So here we have the vector u for I plus 3j. Give a vector parallel. That would be parallel. Yes, any multiple. So here we have 4, negative 3 times any multiple will work. So you could have an example 4, -3. 8, -6 would be fine. Multiplying by 2, multiply by 3. Another example, 12, -9. Do we need we don't need our dot product for this question. Any vector not parallel. Okay? So if you change one of them but not the other, or decide to multiply the top by 5 and the bottom by 2, there would be so many possible answers. But I and j are defined to be unit vectors, right? I is always 1, 0, and j is always 0, 1. Apparently. Orthogonal to you, now we can use the dot product, because we need something so that if we did, so we had the original one is 4, -3, dot product with something in here to equal 0. Again, there's more than one right answer. 0 and 0 isn't actually a vector of any length. So although that's strategic and thoughtful, close. If I did -3 and 4, positive 4 did you mean? Then I would get -12 and -12, and I get -24. 3 and 4 would work. Now, the slope of 4, -3, if you think slope is rise over run, the rise is the y, the run is the x. How do we tell if slopes are perpendicular? They're the flips and negatives of each other. So if one is negative, the other is positive. Notice that here we flipped them. Now the rise is 4 and the run is 3. So these vectors are very close to, like when you write a vector, you're pretty much writing the slope in one way, just that the x and the y is flipped. So you can use that as well to find out if two things are perpendicular. What about 3 dimensions? What would be perpendicular to 1, 2, 3? What could you put in here so that you do the dot product and it would equal 0? It kind of doesn't work that way. 1 over 2 over 3? 3, 2, 1? No, that wouldn't make... Probably what I would do is 3 is my biggest one, so I'd think in factors of 3. Let's just say I put a 3 here and a 3 here. That would give me 3 plus 6 would give me 9. Minus 3 would give me 0. And that would be those two vectors that we just wrote down are perpendicular to each other in 3 dimensions. Okay. This is our last question. Two vectors are defined as vector v, 2j plus xj, 2I plus xj, and wi minus 3j. Find the value of x if they're parallel. So if they're parallel, that means v, which is 2 and x, and w, which is 1 and negative 3, have to be multiples of each other, meaning that they're equal if you put some value of k there. And you can put the k on either side. So it really doesn't matter. If I put the k where I did, can you see that k has to be 2? That's the only way I can make the x parts the same. And if k is equal to 2, that tells me that x has to be negative 6. If they're perpendicular, we know that the dot product has to equal 0. Well, the dot product here would be 2 minus 3x equal to 0. And so, solving for this, x would have to be 2/3. And that's where we'll end.